Hi all, welcome to Heights to Fly. Today we are discussing about some problems related to Euclid's division lemma, that is how to find HCF and some of the proofs related to Euclid's division lemma. It is some questions discussed in first chapter, real numbers in NCERT 10th class textbook, exercise 1.1. Whatever it is useful for any classes relating Euclid's division lemma and how to find HCF. Here the first question is, use Euclid's division lemma to find the HCF of 135 and 225. Here the value of 225 is greater than 135. We discussed the theorem and some problems related to that theorem in the previous video itself. This is some examples only. We have to remember this is value of A and this is value of B. We have to represent these values in A is equal to BQ plus R. So we dividing 225 using 135, 135, 90, 135 into 1 plus 90, again 135 is equal to, represent in terms of 90 into 1 plus 45, again 90 and 45, 90 is equal to 45 into 2 plus 0, remainder is 0. Then what is HCF of 135 and 225? You have to take it as non-zero, last non-zero remainder. The last step, the remainder value is 0. So we have to go to the previous step. The remainder value is 45. So the HCF is 45. Once again, HCF value is taken as last non-zero remainder value. Last non-zero remainder value. In the last step, we get remainder as 0. So we go to the previous step. Here the remainder value is 5. Remainder value is 45. Okay. Let's the next question is, find out HCF of 196 and 38220. Here 38220 is greater than 196. We have to take it as B and this one as B. Our theorem is A is equal to BQ plus R. So 38220 is equal to 196 into. We are dividing 38220 using 196. We get 195. Remainder is 0. 95 plus 0. In the first step, this is a special problem comparing to previous problems. In the first step itself, we get the remainder as 0. So we have to take the value of B itself as HCF. So HCF of 38220, 196 is equal to 196 itself. Okay, here in the first step itself we get the remainder as 0. So we can't take 0 as the HCF value. So there is no previous step also. So we have to take the lowest value, that is the B itself, as the HCF. Next question is 867, HCF of 867 and 255. This is the A and this value is the B. 867 is equal to 255. We have to divide it, 255, and it will become this 255 into 3, 15, 1, 15, 16, 1, 7, 765, 201. So into 3 plus 102. This is the 255 is equal to 102 into 2, that's 51, and we dividing 255 by 102, we will get this value as remainder as result as 2 and remainder as 51. Again this one 102 is equal to 51 into 2, which is equal to 102, so the value of remainder is 0. We get remainder as 0. Then what is HCF of these two values? 102 into 2, here the remainder value is 0, so we have to go to the previous step. Here the remainder is 51, so the HCF is 51. HCF of 867 and 255 is equal to 51. Let's go to another question. Show that any odd positive integer is of the form 6 cube plus 1 or 6 cube plus 3 or 6 cube plus 5 where q is some integer. Once again the question, show that any positive odd integer is of the form 6 cube plus 1, 6 cube plus 3 or 6 cube plus 5 where q is some integer. Let's go to the solution. Let a be a positive integer and the value of b is equal to 6. According to Euclid's theorem, a is equal to b cube plus 6. So the value of b is equal to 6. A equal to b cube plus r. Here the value of b is 6, so the remainder can take values from 0 to 6. That is, r can take value 0, 1, 2, 3, 4, 5. Let's rewrite the equation using b and r. A is equal to 6 cube. The remainder value is 0, so simply the equation is a is equal to 6 cube. Next one, a is equal to 6 cube plus 1. A is equal to 6 cube plus 3. A is equal to 6 cube plus 5. 2 and we skip the value 2 and 4 because in our question only 6 cube plus 1, 6 cube plus 3 and 6 cube plus 5 are included because the value is odd. We can rewrite the values as 2 into 3 cube plus 1, 6 cube plus 1, 2 into 3 cube plus 1 plus 1. When we open the brackets, 2 into 3 cube, 6 cube plus 2 into 1, 2 plus 1. So 6 cube plus 3. Another one, 2 into 3 cube plus 2 plus 1. 6 cube plus 4 plus 5. We can rewrite it as 2 into k1 plus 1, 2 into k2 plus 1, 2 into k3 plus 1, where k1, k2, k3 are positive integers, where k1, k2 and k3 are integers. Hence we can say that 6 cube plus 1, 6 cube plus 3 and 6 cube plus 5 are of the form 6 2k plus 1, 2k plus 1. So right, on k1, k2, k3 we will write it as using variable k. So we can say it as 2k plus 1 where k is an integer. Since all these are adding with values, odd values, plus 1, plus 3, plus 5, we can say that these are not exactly divisible, not divisible by 2. We can say that 6 cube plus 1, 6 cube plus 3 and 6 cube plus 5 are not exactly divisible by 2. Hence we can say that any odd integer can be expressed in the form 6 cube plus 1 or 6 cube plus 3 or 6 cube plus 5. Once again, we represent in this expression all these expressions in the form 2k plus 1. Then we can say that 6 cube plus 1, 6 cube plus 3, 6 cube plus 5 are not divisible by divisible by 2. Hence, these three values are odd numbers. Hence, the theorem is proved. 6q plus 1, 6q plus 3 and 6q plus 5 are positive odd integers. Hence, we can say that proved the theorem. I am explaining the same question once again. Three odd numbers, odd positive integers, 6q plus 1, 6q plus 3 and 6q plus 5. We take the first value a as positive integer and b, the value is 6. According to Euclid's theorem, a is equal to bq plus r. The value of r ranges between 0 to 6. We can take the value 0, 1, 2, 3, 4, 5. A is equal to 6q. And from the question itself, we can rewrite the values using b and r. A is equal to 6q plus 1, A is equal to 6q plus 3 and A is equal to 6q plus 5. 6q plus 2 and 6q plus 4 are skipped because we have to take only odd values. We rewrite these values using simplification 2 into 3q plus 1 and we substitute constant values by variables k1, k2 and k3. These values are not exactly divisible by 2. Hence, we can say that these three are odd numbers. And the next question, another question discussed in the text is an army contingent of 616 members is to march behind an army. Okay, next question. An army of 616 members is to march behind an army of band of 32 members. So the numbers given is 616 and 32 in a parade. The two groups are to march in the same number of columns. Here the question requires same number of columns. In the previous video, we discussed a question related same like this. What is the maximum number of columns in which they can march? So we have to find maximum number of columns. So always remember means the same number of or maximum number of like such questions we have to find out the HCF. Don't be confused. HCF for 616 and 32. 616 is greater than 32. So we have to represent 616 in 32. A is equal to bq plus r, which is the Euclid's theorem. So we are representing 616 divided by 32. 32 into 19. 18, 1, 27, 28, 2, 3, 8, 10, 6. 6, not 8 and 19. And the remainder is 8. So this is the value of q and this is the value of r into 19 plus 8. Again 32 and 8. 32 is equal to 8 into 4 and the remainder is 0. So what is the value of HCF? Last non-zero remainder. Here the value of remainder is 0. So we goes to this one. It is in the form of A is equal to BQ plus R. Here also is equal to BQ plus R. Last non-zero remainder is this one. So HCF is equal to 8. This is the result. So we can say that maximum number of columns in the current question is, result is 8. Maximum number of columns is, so we have to maximum number of columns is equal to 8. Okay, and the next question is, let's go to the fourth question, and the question is use Euclid's division lemma to show that square of any positive integer is of the form 3m or 3m plus 1 for some integer m. Once again the question. Use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. There is a hint is also given in the question. Let x be any positive integer. Hint given is x be any positive integer, then it is of the form 3q or 3q plus 1, 3q plus 2. Now square of each of this and show that they can be rewritten in the form 3m or 3m plus 1. Whatever, let's go to the solution. Consider a as any positive integer and b is equal to 3. According to Euclid's theorem, a is equal to bq plus r. So is equal to here the value of b is given as 3 and the value of r lies between 0 and 3. In previous videos and previous section we discussed a lot about HCF and many of the proofs. You can go through that. Comparing to this question, they are simple, so you can easily understand. After going through that, you can come to this question and it will make you simpler. 0 less than or equal to r less than 3. Because the value of b is 3, so the remainder only lies between 0 to 3. We can rewrite the Euclid's theorem as 3q and substitute the value of r. What is the value of r? According to this range, 0, 1, 2. So plus 0, a is equal to 3q plus 0. So we can write it as a is equal to 3q. Next, a equal to 3q plus 1, a equal to 3q plus 2. Then we have to take a square. A square is equal to 9q square. Here, a square is equal to 3q plus 1, the whole square. A square is equal to 3q plus 2, the whole square. So, what is a? This is a 3q, the whole square. This form. This is in form a plus b the whole square. What is a plus b the whole square? Which is equal to a square plus b square plus 2ab. Based on this equation, we can expand this a square plus b square plus 2ab. So the expression becomes 9q square plus 6q plus 1. And this one becomes 9q square plus 12q plus 4. So we can rewrite it as 3 into 3q square. Similarly, this one as 3 into 3q square plus 2q plus 1. This one 9q square. We can split it as 3 into 3, 9q square. Again this one. From these terms, we take common value 3. 3 outside and bracket open 3q square. After taking 3 here, the balance is 3q square. After taking 3, here the value is 6 divided by 3, 2q, bracket close, and the remaining value plus 1. So after expanding this expression, we get it as 9q square plus 6q, which is equal to here. Another expression, we can rewrite it as 3 into 3q square plus 4q plus 1 plus 1. 9q square, 12q plus 3. Here the value 3 plus 1, 4. So from all these terms, we take 3 as common. So 3 common, 3q square plus 4q plus 1. By multiplying this, we only get 3. The remaining 1, 4 is equal to 3 plus 1. The remaining 1 is placed here. So 1, 2, 3. We get 3 expressions. So we can rewrite it as first value. First one as 3 into k1. Second one as 3k2. plus 1. 3. This one is K2 plus 1. Third one 3 K3 plus 1. 3 K3 plus 1. Once again we derive 3 expressions and we generalize it by taking 3 common. So we get 3 expressions. We can rewrite it as first one as 3 into K1. 3K square is taken as a constant K1 and the bracket, and in the second expression the bracket term is taken as another constant K2, and the third expression the bracket term is taken as another constant. So we can write it as K1, K2 and K3 are some positive integers. So in the given in the hint section 3m or 3m plus 1, like that there is hint is given in such a manner. So we can say that based on that we can say that square of any positive integer is either of the form square of any positive integer is either of the form 3m or 3m plus 1. Okay, let's go through the question, and there is a hint is given and we go through the solution using Euclid's theorem. Some expansions are going through. After that we derive some constant expressions, hence the solution is proved. Okay, next and the last question in this session is another proof, and the question is use Euclid's division lemma, show that the cube of any positive integer is of the form 9m plus 1 or 9m plus 8. In the previous question we discussed about square of any positive integer. Current question we are discussing about cube of any positive integer, and there is a little bit difference in this expression. Let's go to the solution. In the previous same as in the previous question, a is any positive integer and the value of b, it can be taken as 3. According to Euclid's theorem, a is equal to b cube plus r, q greater than or equal to 0. We know that 0 less than or equal to r less than 3. So r can take values from 0, 1, 2. Okay, so we can, based on this values, we can rewrite a as 3q, a is equal to 3q plus 1, a is equal to 3q plus 2. We can take it as case 1. Case 1, a is equal to 3q, we have to take a raised to 3, which is equal to 3q the whole raised to 3. So 27 q raised to 3. Okay, wait here. And then the question itself, it is given in the form 9m plus 1, 9m plus 8. So we can rewrite it using 9 as common. 9 into 3q raised to 3. By multiplying these 9 into 3, we get 27. So 9 into, this is a constant term, we can take it as m. Okay. And case 2, consider this as case 2. Here a is equal to 3q plus 1. So a raised to 3, it is equal to 3q plus 1 the whole raised to 3. We know a plus b the whole raised to 3 is equal to a raised to 3 plus 3 a square b plus 3 ab square plus b raised to 3. What's a plus b the whole raised to 3 equal to a raised to 3 plus 3a square b plus 3ab square plus b raised to 3. So using this expression, we can expand this. We get it as 97q raised to 3 plus 27q square plus 9q plus 1. Okay, you can simplify it as, here we take 9 common, so we have to take 9, 3q raised to 3 plus 3q square plus q, the remaining one outside the bracket. So we get it as 9m plus 1 method. Once again, equal to 3q plus 1, 3q plus 1 the whole raised to 3. We get this expression 9 as common from the first 3 terms and the remaining one outside the bracket. The bracket term is taken as a constant 9m plus 1. And we go to the last case, case 3. Case 3, where a is equal to 3q plus 2, 3q plus 2 the whole raised to 3. We get the expression as 27q raised to 3 plus 54q square plus 36q plus 8. We rewrite it as 9 into 3q raised to 3 plus 6q square plus 4q plus 8. We can rewrite it as constant term 9 into m plus 8. Okay. Hence, proved that, what we proved? Cube of any positive integer is of the form 9m plus 1 or 9m plus 8. Once again, the question given is cube of any positive integer is of the form 9m plus 1 or 9m plus 8. We taken a as a positive integer, b is equal to 3. The value is given, a is equal to Euclid's theorem, a is equal to bq plus r. And the value of r remains 0, 1, 2, a equal to 3q, a equal to 3q plus 1, a equal to 3q plus 2. Based on this condition. First case, we take a raised to 3. So we get it as 9 into m, the first condition given in the question. And case 2, similarly, we take the cube root, cube of the constant, and we get it as 9m plus 1. And the last case, similar case, 9m plus 8, hence the solution is proved. Today we discussed about Euclid's theorem and some of its application, like find HCF of two numbers and one application problem. In the previous video we discussed about Euclid's theorem thoroughly, and here we also go through some proof. So like square of a positive integer and cube of positive integer, like that. And thank you for watching. Thank you for watching. Please subscribe and share for new videos.